Good afternoon to all. It gives me immense pleasure to extend a very warm welcome once again to the national seminar on influence of electronics in instrumentation and trends in VLSI design, organized by Department of Electronics in association with IQAC of St. Thomas College Autonomous, Thrissur. Now it's time for the second technical session. We are having a wonderful person, Mr. Ajal AJ, CEO, IMET Solutions as our resource person. He has an expertise of 15 years in academic session, shouldering various positions in different institutions. I am sure his expertise will help the participants to acquire a little bit of his knowledge. I request Mr. Ajal AJ to handle the technical session. Over to you, sir.
So, very good afternoon to one and all present over here. So, thanks for your warm welcome for this national seminar. So, in today's session, what we are going to discuss is all about the trends in VLSI design. We discuss something regarding the custom of designing. Then we switch over to the historic architecture, how VLSI design came into its existence as of now, and the trends in the VLSI design, and some generic doubts regarding what exactly the industrial requirement of VLSI design. As we know that the electronic industry is booming day to day. And finally, we will try to answer some of your queries. So first of all, what we are going to do is that we will discuss about what exactly the VLSI design is. Generally, as far as an electronics students, you might be knowing about different type of passive and active devices. So we discuss something regarding these devices and how these active devices or passive devices like the so-called RLC circuits, resistance, inductance and capacitance have made a tremendous impact in our VLSI industry. So today, first of all, I will brief out the historic representation of what VLSI design has made to us. So I'm going with my slides over here. The fundamental idea regarding the trends in VLSI design way back with vacuum tubes and certain point contact germanium transistors. In 1947, Barden, Brattain and Shockley made out the innovative discovery of our so-called transistor, and the first integrated circuit, or in short IC, was made out by Jack Kilby in 1958 of Texas Instruments. Now you can see the pictorial representation of the wonder child of electronics, that is nothing but our transistor. It happened in Bell Labs in 1948, as we know that our country has got our independence. Now, in 1958, the primitive model of the first IC or integrated circuit developed by Texas Instrumentation was as shown here. And now the changes has been made out from 1971 onwards. The so-called integration, starting from small scale integration, it operated with a 1 megahertz operation cycle with Intel's 4004 microprocessor towards 8080 microprocessor in 1974 with 4500 transistors. Now, the Intel Pentium 4 generation microprocessor made out with 2000 has made 1.5 gigahertz as the clock cycle, or the modern chip has made out even the breakthrough innovations in nanometers. Now you can see the scale from 2003, 5, 6 and the latest 65 nanometer technology, where the clock gating has been made out with nested supplies. And now, since we are going with the gaming platforms, we had graphic processors, multi-core low power processors, and now even the so-called mobile processors. As we dated with the first ever law of VLSI design by Gordon Moore in 65 has made out that the number of transistors that is multiplied or doubled every 18 to 24 months. So, according to Gordon Moore, the twice the number of transistors, that is approximately every 2 years or even 18 months, has came to a reality. Now, the statistics of the graphical representation gives out a Ohm's law curve, which is a straight line curve, and that satisfies what the Ohm's law is correct till dates. Now, the range of this transistor count has been moved out from a given one or two digit number towards billion trillion number of transistors with different core processors. Now we call it as multi-core processors starting from Pentium Pro 2, 3, 4, etc. A standard cell, coming to a basics, has its own layout, and the standard cells example, we have gone with n number of digital logics such as NOR gate given over here, and the XOR gate has been depicted as shown below. Here you can see the layout or the physical layer designing where the ground to the VDD or the supply has been given out. Now, a standardized cell layout with a different number of rows and channels has been mentioned as shown here. So you can see here 8 rows and 8 channels in a standard cell layout. Here, the so-called embedded system design, which provides multi-core processors, has been depicted as shown here in the given processor. We discuss about the GX style tile. Here you have UART, the PCI interface, flexible IOs, memory controllers, and the network IOs. Now we discuss about the scale of integration starting from 1958 towards 2018. So the Intel processor has been start out the so-called very large scale integration with a basic structure that is 108 kilohertz. Now it is in gigahertz. Now, the integration as far as Gordon Moore has been discussed with SSI or the small scale integration provided 10 gates, and it has been improved with the MSI which has 1000 gates, and now we are going with LSI, VLSI, ULSI, and even giga scale integration. As of now, the VLSI or very large scale integration has been gated with 10K gates, and the statistics you can shown in the depicted diagram gives out the actual value of communication. It gives out our spectrum, first generation, second generation, third generation, and fourth generation systems. Now, the focus area has been shifted. There is a paradigm shift from VLSI to ULSI. We call it as ultra large scale integration or the so-called nanotechnology. It is having a scaling of 10 raised to minus 9 compared to our VLSI technology, which is even lesser, that is 10 raised to minus 6. Now, even higher level of scaling called as gigascale integration are being done. So this is the entire signification of SSI to ULSI, where you can see the number of transistors and number of logic gates. Now, we will be switching over to a small video so that you can better narrate what exactly the so-called VLSI design is.
All chips start out with a very simple raw material, sand. Sand is primarily made up of silicon dioxide or silica. Silicon is the second most abundant element in the Earth's crust, but is only ever found as a compound with oxygen. Complex chemical and physical processes are required to ensure that silicon crystals meet the high production standards that apply to chips. To convert silica sand to silicon, the sand is combined with carbon and heated to an extremely high temperature to remove the oxygen. A number of other steps are required to create the finished product, namely an extremely pure monocrystalline silicon ingot called a boule, with only one impurity atom for every 10 million silicon atoms. Silicon boules are fabricated in a range of different diameters. The most common sizes are 150, 200, and 300 millimeters. Wafers with large diameters offer more space for chips. Extremely thin wafers are then cut from the silicon boules using a special sawing technique. These wafers are the basic building blocks for subsequent chip production. Silicon is a semiconductor. This means it can conduct electricity and also act as an insulator. Its atomic structure looks like this. Every silicon atom has 4 outer electrons. There are no free charge carriers. As a result, the pure monocrystalline silicon is non-conductive at room temperature. To allow it to become conductive, small quantities of specific atoms are added as impurities to the wafer. These impurity atoms must have a number of outer electrons that is either one more or one less than that of silicon. Silicon is in the 14th group of the periodic table of elements. This means that elements in the 13th or 15th group have to be used in this process, referred to as doping. Boron and phosphorus atoms are the most suitable elements in these groups. They are very close to silicon on the periodic table and therefore have very similar properties. Phosphorus has 5 outer electrons. When it is inserted into the silicon crystal lattice, the 5th phosphorus electron can move freely. This means that the silicon phosphorus crystal is N-conductive. In contrast, boron atoms only have 3 outer electrons. When they are introduced into the silicon lattice, one silicon electron has nothing to bond to. This creates electron holes. The holes move through the crystal like positively charged particles, making the material p-conductive. Transistors are built on the p and n conductive layers that exist in a doped wafer. Transistors are the smallest control units in microchips. Their job is to control electric voltages and currents, and they are by far the most important components of electronic circuits. Every transistor on a chip contains p and n conductive layers made of silicon crystals. They also have an additional layer of silicon oxide, which acts as an insulator. A layer of electrically conductive polysilicon is applied on top of this. Every transistor has 3 terminals. The middle one is attached to the gate, which is the electrically conductive polysilicon. If an electrical charge is applied to only the 2 outer terminals, electricity cannot flow as the transistor is blocked. This changes, however, if an additional charge is applied to the middle terminal. Electrons from the p layer are then pulled toward the middle terminal and accumulate at the area bordering the silicon crystal and the insulating gate oxide. A channel then forms underneath the gate between the islands of N-conductive material. Electrons can now flow through this channel. The electrical circuit is closed. In this way, the transistor can be switched back and forth between current enable and disable, between 0 and 1, on and off. But how are these layers created on a wafer? The process to manufacture chips from a wafer starts with the layout and design phase. Highly complex chips are made up of billions of integrated and connected transistors, enabling sophisticated circuits such as microcontrollers and crypto chips to be built on a semiconductor surface measuring just a few square millimeters in size. The sheer number of components calls for an in-depth design process. This entails defining the chip's functions, simulating its technical and physical properties, testing its functionality, and working out the individual transistor connections. Special design tools are used to draw up the plans for integrated circuits and develop a three-dimensional architecture of sandwiched layers. This blueprint is transferred to photomasks. Providing geometric images of the circuits, the photomasks are used as image templates during the subsequent chip fabrication process. To ensure that the microscopic structures of a chip are reproduced flawlessly, they have to be fabricated in a dust-free environment with stable temperature and humidity levels. In other words, they have to be made in a clean room. A clean room is a room in which no more than one particle of dust larger than 0.5 micrometers is permitted in around 10 liters of air. This is even cleaner than the air in an operating room. The ventilation, filtration, and supply systems in a clean room therefore have to be extremely sophisticated. Several million cubic meters of air are circulated every hour, and hundreds of air volume regulators maintain a constant air flow. Employees in these production areas have to abide by an extremely strict dress code. They are not permitted to smoke before work or wear any makeup or jewelry. Cleanroom production areas can only be accessed through a special airlock. Chips are built on a base wafer cut from a silicon boule. Depending on their size, several dozen or several thousand chips can be fabricated on one wafer. First of all, the surface of the wafer is oxidized in a high-temperature furnace operating at approximately 1000 degrees Celsius to create a non-conductive layer. Then a photoresist material is uniformly distributed on this non-conductive layer using centrifugal force. This coating process creates a light-sensitive layer. The wafer is then exposed to light through the photomask in special exposure machines known as steppers. During this process, coaster-size areas of the chip template, known as reticles, are used to transfer the complex geometric patterns of the circuit design to the silicon wafer. The exposed area of the chip pattern is developed, revealing the layer of oxide below. The unexposed part remains as is, protecting the layer of oxide. After this, the exposed layer of oxide is etched off in the areas that have been developed using wet or plasma etching. With plasma etching, special gases bond with the substrate to be removed in the reaction chamber. This enables microscopic layers to be removed in the windows that were exposed and developed in the previous step. Once the photoresist residue has been stripped and the wafer has been cleaned, the wafer undergoes further oxidation. Electrically conductive polysilicon is deposited on this insulation layer. Then photoresist is applied again, and the wafer is exposed to light through the mask. The exposed photoresist is stripped again. Now the polysilicon and the thin oxide layer are etched off. These two layers only remain intact in the center under the photoresist. The next step is the doping process, where impurity atoms are introduced into the exposed silicon. An ion implanter is used to shoot impurity atoms into the silicon. This changes the conductivity of the exposed silicon by fractions of a micrometer. After the photoresist residue has been stripped, another oxide layer is applied. The wafer undergoes another cycle of
So I can hope that the video presentation has given you an insight regarding what exactly the entire procedure, that is starting from the physical layer layout, that is from the software orientation towards the high-end level, that is we are moving towards a clean room technology. You might have seen a person moving towards a clean room with that much specifications, that is they will be having their own buggy dresses. We call it as buggy dresses, and that buggy dresses makes them cleanliness, and they told that we should have a clean environment in order to make out such a VLSI design environment. So the design environment is made in such a manner that a packet dress is made out, and there will be proper aeration that makes the design a final end point. Now, what we are going to do is that we are simply moving out how the design aspects are taken care. The fundamental idea in taking the design aspect is that you have to know the first of all programming part. As a programmer, you should know the HDLs or the hardware description language. We have VHDL, similarly Verilog, and the third one is known as the system Verilog. These are the softwares that are used as EDA tools so that you can have a number of patternization, and from that patternization it is much better in order to make out a design layout. Many type of design tools are available, and we discuss about these design tools in detail. And now we are moving towards the entire part of our presentation. We were discussing something regarding the places of integration. Now, in the case of our clean room technology, there is a low level of environmental pollutants is required. We have already discussed in our video regarding the clean room. Many of the companies like Apple, IBM, and AMD are there from 2009 onwards, which are getting a cumulative percentage of turnover around 60 percentage in the globe. And now the question is why the technology is being scaled. And number of applications are now in portable gadgets like our cellular phones, laptops, and hearing aids. The basic requirement is in order to get into low power consumption and a cheaper development. The first power part is the low power VLSI design. That is in order to go with our lithium ion batteries. Unfortunately, nowadays the battery technologies are much more expensive and the duration is less. Even now, Tesla has bought out the car with electric vehicles, and similarly, many amount of electric vehicles are there where the storage capacity of the battery is now a bottleneck or the constraint. So the scaling and technology node starts in 1971 with a 10 micrometer, and now it ranges from 2020 up to 5 nanometer. Each time a transistor is scaled, we say a new technology node has been introduced. The minimum channel length of the transistor technology node right now is 0.18 micrometer to 90 nanometer. Now, there is a big question regarding that why BJT is not taken for our integration. Other than that, we are using MOS or metal oxide semiconductors. So in 1963, Fairchild unveiled the first logic gate with N channel and P channel transistors. We call it as NMOS transistor and PMOS transistor. And finally, it has been clubbed together or joined to the so-called CMOS or the complementary metal oxide semiconductor technology as of today. So the advantage is it draws almost zero static power dissipation. Now the question is regarding NMOS and CMOS, how you can make out into a low power VLSI design. By the proper design of the NMOS and CMOS, we have made out into different type of MOS channel transistors. Even now we are using bi-CMOS transistors for the high-end transistors. So scaling and its continuous enhancement has made the complementary metal oxide semiconductor as the best suitable scaling device right now in the industry. Now you can go with the overview of the processing technologies. So you can see from the pie diagram, the CMOS has the major share in the market and it is the cash cow with 90%, and the remaining is by CMOS with 5% and bipolar technology around 2%. Gallium arsenide technology is less than 2%. Now we are going to discuss about the VLSI design cycle. It starts with the specification of the spec, the system specification from the industry. So the industry will demand the requirement, and now the entity test will be taken by the architecture design. The architecture gives a CISC type of architecture and reduce the instruction set systems like RISC system. Anyhow, in the VLSI design flow, we go with the RISC architecture due to its lesser complexity and its adaptability towards a given design. Now after that, the circuit design is taken out and we go with the major part, that is a physical layer design. In the physical layer design, it starts with the partitioning, then floor planning, placement, and the timing or clock skew synthesis. After the closure of the timing, the physical layout is over and we go for verification and debugging process, which is nothing but our C program or Python language that we generally use. In the case of a C program or Python language, there will be a debugger, and from that debugger you will be getting the required bugs and you can get the answer, that is the solution. So identification of the bugs and its rectification will be the validation cycle, or we call it as the physical verification cycle. And now once the physical verification cycle is over, eventually it is going for the fabrication stages where we go for the actual fabrication of a IC chip. Now after the fabrication process, that is starting from etching towards all the metallic process is over, the fabrication move towards the packaging and finally testing, and the chip is being ready. Here 80-20 rule is being applied for final testing of a given IC chip. In the case of IC fabrication, you can see in the right column the complexity of how an IC is being placed and the partitioning is being done. Now you can see n number of layers like a multi-story building where you can see the initial layer as a substrate layer, then a buffer layer, and finally undoped silicon layer where you can have three things, three leads, that is the source, gate, and the drain pins. In the case of the chip fabrication process, it moves like the silicon wafer manufacture with an epitaxial growth, and now after the growth has been started, it go with n number of chemical processes. As we studied in chemistry, there will be oxidation and reduction process, and finally we go with a light, that is a photolithography. That is, a photo means light and litho means a stone, graphy means encryption. And by encrypting the given data by using the light ray, that is the UV radiation, to enter into the chip, we go for the etching process, and finally either the ion implantation process known as the diffusion or metallization. Once these processes are over, it is ready for packaging to the industry. Now the entire process gives the manufacturing with a CZ process or FZ process or Bridgman process. These are different nomenclature for silicon wafer manufacturing, and we go with the wafer manufacturing process with MBE, that is molecular beam epitaxy, or MOCVD, that is crystal vapor deposition. After that, we generally go with oxidation, or then we go with the patterning, that is the floor planning part. We generally go with the patterning with a lithographical path, and finally after the 80-20 rule is being applied, we generally go with the removal or etching of a given VLSI circuit. Now the entire process is being carried out by using diffusion or ion implantation process. After that, activation of the implanted dopants by using annealing can be done, and finally we call it as metallization or sputtering effect, and the test assembly and packaging section is the final part in chip fabrication process. So you can see the pictorial representation, that is number one, the crystal growth, that is we generally take the sand to silicon process and the seed crystal is taken out, and we will be having a single crystal ignot that is up to 9-meter length. Now this ignot is trimmed or cut into different flat rendering surfaces so that the fifth portion, that is the wafer slicing, is being carried out. In order to slice out in a proper manner, we go with edge rounding and lapping process. Final stage is wafer etching, and polishing is done out in utter clarification so that no any IC is get damaged. And final part, or the most important part, is verification or wafer inspection part. Once the crystal is polished, you can see the face of the person in the given crystal lattice. And if you are closely watching the crystal, you can see a yellow color shades where the crystal lattice are not being used there. So there is a 80-20 rule by which the 20% of this given part or area is unutilized. This is said to be the bottleneck of crystal or wafer growth. Now we go with the wafer processing, where we go with the different type of names. One is known as PVD. We call it as physical vapor deposition, or CVD, chemical vapor deposition. Nowadays we are using ECD, or electrochemical deposition, or ALD, in a higher atomic layer deposition. Anyhow, these are the general or the basic methods for wafer processing that is being used. Finally, modification of the electric properties has been done, and we generally go with a dynamic process known as RTA, rapid thermal annealing, and after that we go with the oxidation and the so-called modern electronic gadgets like the mobile phone. If you are taking an X-ray of our body, you can see the bones. Similarly, if you are taking an X-ray of the mobile phone, you can see the RF signal. Similarly, the RF power, and an IC for power management, what we call as a low power IC. And similarly, we will get an analog and a digital baseband, which is our DSP, or digital signal processor, and an controller unit known as MCU. And now the industry trends has been moved out. Now we will be having n number of electronic gadgets, starting from our notepads even to our headsets. So high performance, low power dissipation wireless chips are being used, so that ultra high speed design without any delay for interconnectivity is made. And the challenges in digital design includes the low power, number two, the power dissipation and reliability. And the MBA concept known as just in time or time to market also prevails, one among the greater challenges in digital design. Now you can see the graph regarding the productivity trends, and you can see the scaling out, the complexity outspaces the design productivity. Nowadays, we can have to make out such a trend that the complexity outspaces design productivity. Now, the major advantage is that as a design engineer, you can go with a CAD architecture, so called as computer aided design. The need for ultra fast design methods made design automation a wonderful area. The Silicon City, called as Bangalore, has n number of job opportunity for the design engineers. The design abstraction enables CAD into the basic level, system level to module level, and it downgrades to gate circuit levels. So the entire architecture is in a top-down approach from system level towards the individual or the specific level based on the basic ingredient of a given architecture. Even nowadays, a bottom-up approach is also being utilized. The simplified VLSI design flow has three basic domains. We call it as a behavioral domain, number two, the structural domain, and the third one is a physical domain. So the layout has been moved out for verification, starting from the circuit design. So basic requirement is the logical design part, and from that you can go for circuit verification, and finally the physical design and layout for verification part. Now, if you go with the block discussion, you can discuss about the FPGAs, that is the field programmable gate array. At the ends, you will be having IO blocks, and there are n number of CLBs, that is the configurable logic block. It's a very important thing that as a beginner, you can start with a FPGA or field programmable gate array, so that you can design a CLB, that is the configurable logical block. From this, the design metrics includes number one, the speed, that is the latency, delay, operating frequency. Number two, the power dissipation. Number three, the design time and effort, which is based upon the cost. And last and the most important one is reliability, that is its process, voltage and physical variations. We generally discuss the physical variation under the brand temperature variation. Even though there is given data is regarding temperature variation, all the physical parameters starting from temperature, pressure, melting point, boiling point, everything matters in the case of reliability is concerned in design metrics. We discuss about a full custom design where the complete fabrication process is taken by manual design. It gives you total flexibility and the very high development cost due to smallest die area, and the features includes cheap only at highest quantities. We know that the Silicon Valley that is available in National University of Singapore NUS provides the cheapest and high quantity or high quality feature of full custom design. Now the full custom design has given a top view with the anvil, its metallic wire, the poly diffusions and its contacts. We can see a dog legging here in full custom design. The cost of integrated circuit based upon NRE, it is a non-recurrent engineering cost. That is a one-time cost factor like all the software is having, and there are different recurrent costs including the prototype, the packaging, testing and the chip areas proportion. Now the die cost depends upon a single die. We will be having a wafer which is going up to 30 centimeter. That is the yield can be given with a mathematical calculation, number of good chips divided by total number of chips per wafer into 100 percentage. So you get the yield in percentage, and the die cost is nothing but wafer cost to the die per wafer and the die yield. Now the major drawback is regarding the defect. You cannot predict 100% efficiency, so the yield factor will be given out and the defect should be rectified. The mathematical formula depicts the defect that is available in the case of yield. The defect should be much less for a better reliability of a given system. Now, different type of loads has been given out like inductive coupling, capacitive coupling, and the filtering circuits that provides the power into lesser noise value. That is, the noise reduction or suppression is much important in order to get the reliability engineering part in digital integrated circuit. We know that the bandwidth of noise is supposed to be infinity in any design. In basic or fundamental physics, we discuss noise as a bandwidth of infinity, so that the noise margins that should be remained in a cutoff region. So the noise margins should be less so that the gate input and output time makes the low noise margin, so that we will be having two activities. One is the fan in and fan out. That is the fan in is based upon the input and fan out based on the output, which depicts the efficiency as a parameter of VLSI circuits. So an ideal gate should be giving you a square or a rectangular signal, which is not in the case of our real signals. So there will be a change from the ideal characteristics due to delay. That is nothing but our propagation delay. And this propagation delay gives out glitches and unwanted noise performance in a given system. So the delay should be reduced, or the propagation delay of each gate should be reduced such that you can get the ideal characteristics of a gate where the V in and V out, the V characteristics can be in a better ideal state. Now, the next part is regarding the top 10 VLSI companies in India. The number one company based upon VLSI design established is the Texas Instrumentation. Texas Instrument, it has its corporate office in Dallas in United States, but it also has its unit in Bangalore. Second one is Analog Device. It is having a corporate office in USA, again has its base in Hyderabad. And the third one is Cyprus Semiconductor Corporation. It's also established in 1982 in US, has its office in Delhi. And fourth one is Broadcom Corporation. It's also in US, but we have the manufacturers in India too. Based upon the VoIP or GPS, they are much more going with a 3G, 4G, and 5G adaptation of wireless networks. And the fifth one we know about Cisco systems used for routers, switch, hub, etc. is having their office, corporate office in San Jose in US, has its office in Bangalore. And the sixth one is Bitmapper Integration Technologies, has its corporate office in Pune, Maharashtra, established in 1985. And seventh one is Horizon Semiconductors. Its corporate office is in Bangalore, Karnataka, which has been established in the year 1815, long way back, which provides Blu-ray, transcoder, encoder ICs, HD channels, etc. And it is one among the top semiconductor companies in India. And the eighth one is Infochip Limited, having its corporate office in Ahmedabad, Gujarat, is among the top 10 VLSI companies in India. Ninth one is Trident Tech Labs, having its corporate office in New Delhi, established in the year 2000. It is based on different type of scales of organization where the VLSI signal processing is being done in Trident Tech Lab. And the 10th one is HCL Technologies, started with the Chennai-based company, having its engineering college known as Siva Subramania Nadar College, SSN in Chennai, has its corporate office in Noida, Uttar Pradesh. These are the top 10 VLSI-based companies that is available in our native. Now, for your reference, we are recommending some books. Based on that, some recommended books are VLSI Technology by SMC and Silicon VLSI Technology by Plummer. I can give you certain other details regarding VLSI physical design and CMOS VLSI design by Neil Waste. So, I will just place my design constraint regarding the VLSI physical design. So, what exactly do you mean by the term VLSI physical design? So, we discuss the VLSI physical design as a basic structure of our IC design and fabrication industry. It's also a book review regarding the VLSI physical design by Andrew B. Kank, and it's one of the best books available in market regarding VLSI physical design. I will just give out how graph theory, mathematical orientation, partitioning, and the timing analysis has been detailed in this book. So what as a student or a faculty we can go with this book. So the introduction part is regarding the IC production based on the CAD tools. We have different type of VLSI CAD tools like VHDL, Verilog, and System Verilog. These software tools are using sophisticated algorithms which can give out NP hard problems. So graphs, algorithms, and certain design communication theories are being used so that the complexity or computational geometry is reduced. So from the year 1950 onwards, the electronic design and automation industry has been boomed out, and the manual design started with 1950, and way back to 1985, the first performance tool of parallel optimization started with a better understanding of graph theory gives out the reduced complexity structures in VLSI design. And in 2000, the first 3D multi-layer placement routing techniques were developed, and from 2020 we had DFM and OPC, we call it as design for manufacturability and optical proximity correction tools has been designed. As we discussed already regarding the VLSI design flow, the physical design gives out starting from a top to bottom end, partitioning, chip planning, placement, and end with a time closure and opening algorithms. Now, if you are going with a software package, you will be having a layout editor where you will be having a menu bar and toolbar or a drawing tools. And from that, you can take out, it's like a pick and place. If you are having the hardware VHDL knowledge, you can go with the physical layout design in a very much better. And generally we go with these type of logic gates and or nor NAND or inverters. We know the truth table from the basic level. The common digital cells are included, and finally this and or boolean logics has been moved out with a contact metal layer, different type of poly layer, diffusion layer, and p or n type transistors. Now the power rail has been introduced and the ground rail, so that the entire layout will be screenshot like this, and you can see the much closer view of design layout. Now the design styles are fed through different pads and standard cells, and we have certain power pads for our standard design OTC routing or over the cell type of routing. Now we can also make out the design with a layout of macro cells where you will be having a RAM, that is our random access memory, PLA, the programmable logic array, or PLD, programmable logic devices. After that, routing regions are given out so that the power dissipation of these macro level cells are made possible. If you have a field programmable gate array, it will be like different types of LBs and SB that are blockwise placed. These lookup table blocks are connected with a different type of roads. And finally, metallization has been done out for the external connection. We will be having different type of polysilicon, metallic, and the supply layout where they are aligned in a manner that these are all supplied without having any interconnection, so that the low power VLSI design constraints are carried out. There are appropriate contact and wire for the types of constraint. We are having basically different type of constraints, starting from the technology constraints. That is, we should have minimum layout width which is spacing out the layout shape, and second one, electrical constraints including the maximum timing constraint which gives out the signal delay, and last, the design methodology or constraint. Basic algorithms are available which are said to be heuristic algorithms that gives out the mathematical or graph theory. We discuss about constructive and iterative graph, so that the algorithm and its complexity can be made terminated as far as the criteria has met. Graph theory based upon hypergraph, multi-graphs are made out, and directed graphs with cycles and acyclic graphs are used, so that even a basic mathematical modeling, a person who is having mathematics as his degree can go with this VLSI design. We have undirected graphs and directed T graphs, so that the routing we call it as RMST, that is rectilinear minimum spanning trees can be made out, and a netlist can be provided. From this netlist we will get a connectivity graph and a connectivity matrix. By solving this, we will be having a Euclidean distance or Manhattan design, and these distances are made so that least possible design is made out for EDTA terminology. So this is the generic view of our VLSI physical design book regarding that of Andrew B. Kang. So I hope that things are much more predictable and realistic for you. Now, I can wind out my class or my session over here. And if you have any queries regarding VLSI design, fabrication procedure, you may now ask. So if you have any queries regarding VLSI design, its architecture or flow diagrams, you may now ask so that I may be able to solve your queries. I think I have to switch back to the conveners of the program. If you have any queries regarding that, you can ask now. Hope I think that the concept might be clear. So I will be switching back to the conveners for their session end.
Thank you, sir. That's the end of our second session. And thank you for your insights. It was a knowledge-packed session. We have been listening to ME speakers deliberating the areas of instrumentation and VLSI. Now we have come to an end national seminar. Influence of electronics in instrumentation and trends in VLSI. I extend my sincere gratitude to Mr. Ajal AJ, CEO, IMET Solutions, for accepting our request despite of his schedule. I must thank the person who provided the technical support throughout the day. Once again, I thank Krishna Nelson for help supporting us and all for the success of this event. Thank you all.
So I thank the management of St. Thomas College, the HOD of Electronics Department, the organizers, and all the supporting faculty for inviting me and making this session a really worthwhile session without any interruption. Thank you all.